Now moving on with this global positioning system problem, in part A we calculated the intensity a GPS receiver receives when it's directly below the satellite. Part B, what are the amplitudes of the electric and magnetic fields at the GPS receiver in part A, and how long does it take the signal to reach the receiver? Now, the pointing vector S is equal to 1 over mu 0, 1 over mu 0, E cross B. The average value of the magnitude is the intensity, which is 1 over 2 mu 0 E max squared over C because B is equal to E over C, so it is E max over E max squared over 2 is the time averaged value of E squared. So we have time averaged value of E is E max over square root 2. And B is, magnetic field is, electric field component divided by C. That's what we obtained from Maxwell's equations. So we can write E max, the electric field amplitude is 2 mu 0 speed of light times intensity square root and B max, the maximum magnetic field or magnetic field amplitude will be 2 mu 0 I divided by the speed of light square root. So that's E max, that's B max. And how long does it take for the signal to reach the receiver? Well, the signal travels a distance h, the altitude above the ground, with the speed of light c. Therefore, it takes h over c time. Now we can calculate the numbers. E max is equal to 2 times 4 pi 10 to minus 7 permeability of free space, 3 times 10 to 8 meters per second speed of light, 9.75 10 to minus 15 watts per meter squared, the answer from part A, and all this inside the square root. And from this we obtain the maximum electric field to be 2.71 times 10 to minus 6 newtons per coulombs. And now we can calculate the magnetic field. B max is simply E max divided by C. So this gives us a maximum magnetic field magnitude of 9.03 times 10 to minus 15 Tesla. And as for the travel time for the signal, T is equal to H over C. The altitude we have calculated in part A to be 2.02 times 10 to 7 meters. The speed of light is 3 times 10 to 8 meters per second. And the travel time is then 0.0673 seconds. That answers part B. Part C, if the receiver is a square panel, A is equal to 1.5 centimeters on a side that absorbs all of the beam. What average pressure does the signal exert on it? We have complete absorption scenario. The average pressure exerted on this panel will be the average value of the pointing vector magnitude S average divided by C for complete absorption, as we have seen many times in the previous problems. So the mean pressure it exerts on the panel will be the intensity 9.75 times 10 to minus 15 watts per meter square divided by the speed of light 3 times 10 to 8 meters per second. So this gives us a mean pressure of 3.25 times 10 to minus 23 pascals. Okay, so how did we reach this conclusion? The pointing vector magnitude, the intensity, is the rate of change of energy flow, dTER dt, divided by perpendicular area. So we see that the pointing vector magnitude times the area is the rate of energy flow, dTER, electromagnetic radiation, dt, which is d dt of f dx, so that's like work, and which is equal to the force multiplied by dx dt, which is the speed of light. So we obtain the average force per area to be S average divided by the speed of light, c. That's for complete absorption. So we have reviewed that result. Part D, what wavelength must the receiver be tuned to? Well, the speed of light, c, is equal to the wavelength times the frequency. So the wavelength is the speed of light divided by the frequency f. So this gives us a wavelength 3 times 10 to 8 meters per second divided by the frequency 1575.42 megahertz times 10 to 6 hertz. So we find that the wavelength is 0.190 meters. It is simply c divided by f. Okay. So in this part of the problem, first we calculated the maximum electric field and magnetic field components. So using the average value of the pointing vector is equal to the intensity, which is 1 over 2 mu 0 E max squared over c, we can write Emax as square root 2 mu 0 c, the intensity, and Bmax is Emax over c. The travel time is the altitude it travels, h it travels, with the speed of light c, so h divided by c. The complete absorption scenario for the average pressure exerted on the panel is S average divided by C, as we have shown here, and the wavelength can be calculated as the speed of light divided by the frequency. Because the problem asks what average pressure the signal exerts, the area of the square panel here is not important because it's the force per area we're trying to calculate.